Good afternoon, everyone. First, I would like to welcome everybody to another season of our seminar. This year, we have the privilege of welcoming Professor Luis Fernando Messias Franco and his students from Unicam as our new collaborators. Together, we expect to promote meaningful discussions and also the exchange of ideas among academics and students featuring renowned speakers to cover a diverse range of topics related to thermodynamics. Today's seminar has the great pleasure of welcoming Professor Joan Brennecke. Professor Brennecke is currently a Cockrell Family Chair in Engineering at the Makeda Department of Chemical Engineering at the University of Texas at Austin. She began her academic career at the University of Notre Dame after completing her master's and PhD degrees at the University of Illinois. Her research interests are primarily in the development of less environmentally harmful solvents, and these include supercritical fluids and ionic liquids. In developing these solvents, Dr. Brennecke's primary interests are in the measurement and modeling of thermodynamics, thermophysical properties, phase behavior, and separations. She has served as the editor-in-chief of the Journal of Chemical and Engineering Data since 2010, and she was into the National Academy of Engineering in 2012, and recently served as chair of the National Academic Studies on a research agenda for a new era on separation science.
Today I'm going to be talking about the work we've been doing with gas separations using ionic liquid-based facilitated transport membranes. And this is work done primarily by one of my PhD students, Sejun Park, but there's also a little preliminary work by Constanza and a little bit of mixed gas permeability measurements done by Maggie. This is all done in collaboration with my colleague here at the University of Texas, Benny Freeman, who's really the membrane expert. So to go ahead and get started, just talk about what I mean by facilitated transport membranes. And this is actually from a paper by Burju Gherkin, who's one of my former PhD students. She's now at Case Western Reserve. And she published this nice paper using facilitated transport membranes with ionic liquids for carbon dioxide separations. So the idea with facilitated transport membranes is that we're going to put something in the membrane that is selective for one of the components that we're interested in. But in this case, the target gas actually reacts with something in the membrane. And the primary function of doing that is to enhance the solubility. So in this case, she was putting things in the membrane that would react with carbon dioxide to enhance its solubility in the membrane and thus the permeability across the membrane. In the schematic, it shows a very nice range of ways that you can do this. So on the very left-hand side, she has nothing in there that reacts with CO2. So she says this is solution diffusion, and I'll talk about that more in just a couple slides. But that's the primary mechanism by which we believe the permeability of the gas species occurs, in that the gases dissolve in whatever's in the membrane and diffuse across the membrane, right? But everything to the right of that is these facilitated transport membranes, where you then incorporate a moiety in there that reacts with the CO2. And in this case, it's amines. So the amine reacts with the carbon dioxide. So in the fixed carrier case, the amine is actually tethered to the polymer. So it can't move. So the amine can't really move. But the CO2 can react with the amine and then kind of hop from one amine to the next in order to transport across the membrane. In the middle of the diagram where it says mobile carrier, this would be the case where you may have a polymeric membrane, but you dissolve something in the polymeric membrane, which can in fact move. And so, shown here are things like amino acid or piperazine or whatever, some organic molecule or ion that then has the amine functionality that can react with the CO2, but then that whole complex, the species that has the amine, which then reacts with the CO2, that whole thing can diffuse across the membrane. And then the thing on the right is a case in which she shows you a polymerized ionic liquid facilitated transport membrane. And this would be where, for instance, you've got an imidazolium cation, which is tethered to the polymer. So the imidazolium cation can't move, but the anion, and she shows here some amino acid based anions, the anion is the thing that reacts with the CO2, and that anion can in fact move across the membrane. So that, the anions associated with any one of these fixed cations changes as that complex moves across the membrane. So that's what we mean by facilitated transport membranes. And so in this case, she was using it for carbon dioxide. What I'm going to be talking about today is using facilitated transport membranes for olefin-paraffin separations. And pretty much everything I'm talking about the majority of it comes from this first paper that was published in Angewandte Chemie, and a little bit of the preliminary work was in this paper in INEC Research. So the reason why we care about olefin-paraffin separations is that an awful lot of stuff that we use is made from ethylene and propylene. These two olefins are in fact the largest volume chemicals produced annually. And as I said, they're the principal raw materials for a large number of things shown here in the middle. A large number of things that we make in the petrochemicals industry. And in fact, global production of ethylene and propylene exceeds 200 million tons, which corresponds to more than 30 kilograms for each person on the earth. So we do in fact use an awful lot of ethylene and propylene. Now, the problem is that nature doesn't give us ethylene and propylene. Nature gives us ethane and propane. And so we have to make the ethylene and the propylene by, most normally, it's steam cracking, and you end up with a mixture, and certainly it is a mixture of the olefins and the paraffins. And so we have to separate then the olefins that we want to use to turn into additional compounds from the paraffins. And the way this is done currently is by cryogenic distillation. It's a very difficult separation because the ethane and ethylene have very similar properties, very similar volatilities. Same thing for propane and propylene. So the cryogenic distillation is very energy intensive and high capital costs. These columns can have up to 200 stages in them. So overall, 1/3% of all of the energy used in the entire world is used for just ethylene, ethane, and propylene, propane separations. And it's estimated that about 75% of the cost of the olefins comes from doing separations. So we would very much like to do this in a way that is less energy and cost intensive. And so one potential way of doing this is by using membranes, where you don't have to put in all the energy to do a phase change. Unfortunately, there's currently no commercial membranes available for doing olefin paraffin separations. Now, the reason why we're looking at doing this with facilitated transport in a membrane is because olefins can selectively bind with various transition metals. And so what's shown here is silver plus. So the silver and the antibonding pi orbitals of the olefin interact to form a complex. So like the CO2 reacting with the amine, here we'll have the olefin reacting with silver plus. So we're interested in doing this in a supported ionic liquid membrane. And the reason why we want to use ionic liquids is because they have a little bit of selectivity for olefin over paraffins, even when you don't put any silver in there. The ionic liquids, of course, are liquids. So as you diffuse across the membrane, they're diffusing through a liquid, which gives us potentially higher diffusivities than you would have in a solid polymeric membrane. The ionic liquids, of course, have very, very low vapor pressures, so the ionic liquid isn't going to evaporate and change the supported ionic liquid membrane with time. And of course, we can dissolve some of these metal salts that we're interested in. So the silver salts that we want to use for this facilitated transport can be easily dissolved in the ionic liquid. And there is literature evidence for using supported ionic liquid membranes for olefin paraffin separations. So I said that this is still actually a solution diffusion mechanism, and that's what's kind of shown here, that we're going to have a mixture of ethane and ethylene on the upstream side, and they are going to diffuse into the membrane and dissolve in the membrane, but we're going to enhance the solubility of the olefin because that silver can complex with the olefin. And then that complex of the silver plus and the olefin can diffuse across the membrane. A little bit of ethane will also dissolve, but not as much. And so that leads to the increased selectivity of the olefin over the paraffin. So that selectivity is given by the ratio of the permeabilities of the two species. And so then that permeability is written as its solubility times its diffusivity. All right, so if we increase the concentration of the silver salt, we're going to increase the solubility of the olefin in the membrane, and that's going to lead to an increase in the permeability of the olefin, and then increase our selectivity. So yeah, permeability just being diffusivities times selectivity. And as I said, we're not, certainly by far, not the first people to look at using supported ionic liquid membranes for olefin paraffin separations. There's a lot other folks who've done really great work. But what I will show you is that we've been able to develop supported ionic liquids membranes that are stable in the presence of hydrogen. And that's very important because hydrogen is always present because we've made the olefin from the paraffin, like dehydrogenating or cracking the paraffin. So here are some of our preliminary works that Constanza did. And she just used an anapore disc. So this is just aluminum oxide disc. It's got relatively big holes in it. And she just put in the holes a mixture of the ionic liquid. In this case, she used this hexylmethylenedizoleum bistriflamide and dissolved some of silver bistriflamide into the ionic liquid. And so what's shown on the left-hand side is permeability as a function of the transmembrane pressure. So the difference between the upstream pressure and the downstream pressure. And these are just pure gas permeabilities. All right. So the triangles are for, in this case, propylene, and the circles are for propane. So you can see down at the bottom is the circles. So those are the propane permeabilities that are relatively low. And the different colors correspond to different amounts of the silver bistriflamide dissolved in the ionic liquid that's put into this nanopore disc. And you can see that if you look at those circles carefully, the highest permeability of the propane is when we don't have any silver in there. When we start adding silver, the permeability of the propane actually goes down a little bit. And that's actually because when we add the silver salt to the ionic liquid, it increases the viscosity of the mixture. So that diffusivity of the propane decreases a little bit. All right, so you can look at then the triangles. And so you can see that when we have no silver in there, the permeability of the propylene is higher than the permeability of the propane, just because there is a little bit of solubility selectivity of olefins over paraffins in the ionic liquids. But the permeability of the propylene increases substantially when we start adding the silver salt. And you can see that as we go up, in this case, up to 1 molar of the silver salt in the ionic liquid. The corresponding selectivities, which are just the permeabilities of the olefin divided by the permeability of the paraffin, is shown on the right-hand side. All right, so I'm just dividing the propylene numbers by the propane numbers. And so you can see we can get some decent selectivities as we increase the silver salt concentration. Constanza did measure solubilities using our gravimetric microbalance. And so those are shown on the left-hand side. So particularly you want to look at the triangles as you go from having no silver salt present to having the 1 molar silver salt present. You can see the dramatic increase in the solubility. All right, so then we say that, permeability is solubility times diffusivity. So we've measured permeabilities, we've measured solubilities, so we back out diffusivities, and that's what's shown on the right-hand side. And so, as I said, the propane, the circles, all right, as we add the silver salt, the propane diffusivity decreases because the viscosity is increasing. All right, but then I want to draw your attention to the propylene, all right, which is the triangles. And so the highest diffusivity is, in fact, when we have no silver salt present. And then we start adding a little silver salt, and then the diffusivity of the propylene drops dramatically, right? So you can go all the way down to the bottom here, all right? And that's because now the species that is diffusing across the membrane is not propylene. It is propylene complexed with the silver salt, which then has to drag a bistriflamide anion on it to maintain charge neutrality. So you're sacrificing a lot in your diffusivity because you've got a larger species that's having to diffuse, but you still increase your overall selectivity because the solubility has increased so much. All right, so now you know the types of diagrams I'm going to show you. So this is Sejun's work for not propane propylene, but ethane ethylene. He did exactly the same experiment. This is with a 1 molar silver bistriflamide. You can see his pure gas permeabilities on the left-hand side, and then the pink is his selectivities, where those numbers are given over on the right-hand side. All right, and so he said, let's change things around. And so he looked at same cation, but changed the anion. So instead of bistriflamide, we used nitrate, and we keep our anions the same with the silver salt. So we're using 1 molar of the silver nitrate. And once again, you can see the permeabilities. The permeabilities are less. The units of permeabilities that the membrane people use is this thing called bearer. Higher is better, right? And so if you compare that to the previous slide, we're an order of magnitude less in the permeabilities of everybody. And that's simply because the nitrate ionic liquid is much more viscous than the bistriflamide one. But you'll also notice if you look on the right-hand side, the selectivities are lower. And we anticipate, we postulate that the reason is because the silver nitrate is more tightly bound to each other, the cation and the anion. And probably that means that the silver plus is less available to complex with the olefin. All right, so the membrane people love to plot their results on this upper bound plot, where they give on the left-hand side the selectivity that they're of the two gases that they're interested. And once again, this is based on the pure gas permeabilities. So here we've got ethylene and ethane selectivity on the y-axis as a function of the permeability of the thing that you're trying to recover, right? In which case that's our ethylene. And so there's always a trade-off. As you get higher permeability, you tend to get lower selectivity. All right, so what's shown here, the upside down triangles is some polymeric membranes and so on. All right, and the 1 molar silver bistriflamide is over this gold star over here. And they tend to put this upper bound line that goes kind of on the top edge of most of the data that's available in literature. So that's that dashed line. It's essentially empirical. But then if we increase our silver contents even higher, and I haven't shown you that data yet, but up to like 1.7 molar of silver bistriflamide, then we're up here in these red star area. And so these are kind of attractive selectivities and permeabilities above this upper bound, if you will, that people report. So the other thing I want to draw your attention to on this plot are the green squares. And the green squares are actually a facilitated transport membrane that's a polymer. It's this P-Bax polymer where they put silver BF4 in it. And they put a lot of silver BF4 in it, 80 weight percent. And so when they ran it initially, they got this incredibly impressive selectivity and permeability, the one at the very top. But when they exposed it to hydrogen, their selectivities and permeabilities started going down. And that's what the sequence of these green squares are until they basically lost all of their selectivity. All right, so that's what we want to talk about, is that we really care about in these membranes selectivity and permeability. But then another important performance criteria is tolerance to hydrogen. And the reason is because the silver plus, right, our active facilitated transport species, the thing that's reacting with the olefin, can react with hydrogen and be reduced to silver metal, silver zero. And the silver zero is not capable of binding to the olefin. And so this is why this facilitated transport membrane with this polymer that's shown here, there's no ionic liquid here. The thing on the right is just from the literature, which is this polymer with this 80 weight percent silver BF4 in it. And they exposed it to a small amount of hydrogen between measuring it again with the olefin and the paraffin. And you can see that it decreased dramatically, so that within a few days it had really lost its selectivity. So we were interested in what happens with the supported ionic liquid membrane, and this is the work that hadn't been done previously. So initially Constanza did this. So she looked at, so these are her measurements with actually a hexylmethyl methylenedizoline bistriflamide and close to a 1 molar silver salt concentration. And she was really surprised. It looked like the selectivity was going down a bit, but not nearly as badly as what had been observed in the polymeric membrane with the silver BF4. All right. So just to tell you how we do these experiments, we put the supported ionic liquid membrane in this permeator cell, all right, where we control the pressure, the temperature. It's all in a water bath, and control the pressure upstream, and we pull a vacuum downstream and then just watch the pressure increase downstream as the gas permeates across the cell. So what we would do is to load our supported ionic liquid membrane, pull a vacuum, then we would put, for instance, the ethane and measure its permeability, take that out, put ethylene and measure its permeability, and then we would expose it to pure hydrogen. In fact, we did pure hydrogen about 2 bar for a day, and then we would remove the hydrogen, pull a vacuum, and then once again do the ethane and the ethylene. And so these are the measurements that say June had. This is for a 0.5 molar silver bis triple mid, and he did this for a bunch of days. You can see it, he did it a day at a time, and remeasured the, in this case, the propane and propylene permeabilities. And he got very consistent values for those permeabilities and therefore the selectivities, even after exposing it to hydrogen for 6 days. So we thought this was very interesting. Here are his results for a higher silver loading. This is the 1.7 molar, where we got selectivities about 8. And once again, very consistent, stable permeabilities, even when we're exposing it to pure hydrogen in between the olefin and paraffin measurements. All right, so he then had done these measurements with a nitrate, right? The nitrate salt, the silver nitrate in the nitrate ionic liquid, and he got very different results with the nitrate. So if you look at the selectivity, you may remember that the selectivity with the nitrate didn't start out as high, about 3, but as we expose it to the hydrogen, you can see the purple, which is the selectivity, decreasing as a function of time of hydrogen exposure. And also shown on here is the measurements at 3 different transmembrane pressures, and they start out all together, but then after this hydrogen exposure, there's different permeabilities at different pressures. So clearly the membrane is degrading in many potentially complicated ways. So our hypothesis is that the silver plus is being reduced to silver zero in the nitrate ionic liquid silver salt mixture, but not in the one with the bis triple amide. All right, and this is just a reminder of what's happening, that the silver salt can be reduced by hydrogen to make silver zero, silver metal nanoparticles. All right, so say June repeated the experiments with the nitrate using different concentrations of the silver nitrate. So he has one that is 0.9 molar, then 0.5 molar, and then a very low 0.12 molar, and did the same experiments each time, where in between measuring the olefin and the paraffin, he had it exposed to 2 bar of hydrogen, of pure hydrogen. And you can see that the selectivity decreases most rapidly when we have less silver in there. And on the right-hand side, there's actually pictures of the membranes. So when we initially make them, they're clear or white, all right? But as you expose it to hydrogen, they become brown or dark brown or black. So all these results seem consistent with the hydrogen reacting with the silver plus to make silver zero, which is black. All right. He also looked at some of the, did some SEMs of some of the cross sections of supported ionic liquid membranes, and he did find little particles. See, these are actually the little pores of the anapore disc that has the ionic liquid silver salt mixture in it, and he actually did see little particles in the membranes made from this silver nitrate. Ionic nitrate ionic liquid thing, but he didn't see any of these little particles when he had the bistriflamide mixtures. But to look at this more carefully, we said, well, let's get rid of the membrane. Let's just look at the ionic liquid silver salt mixture. And so that's what we did here. We've got a sapphire tube that we can see through, and just pressurize up with hydrogen, so that we could visually observe what was going on. And so here's a really nice comparison of pictures of this. On the top is the bistriflamide mixture, and on the bottom is the nitrate mixture. And so what you're looking at is the sapphire tube. There's a stir bar at the bottom of the sapphire tube, which we, use a magnet to agitate up and down to make sure it's well mixed. And then the little thing you see at the top is the meniscus, all right, of the ion. So below that meniscus is the ionic liquid silver salt mixture. And then we're pressurizing it up with hydrogen. In this case, actually a higher pressure of hydrogen, 5 bar of hydrogen. And so in the bistriflamide case, maybe you're seeing a little tinge of color as a function of time, but in the nitrate case, as soon as we expose it to the hydrogen, it turns completely black. And just to tell you, the reason why the levels, the meniscus go down is because Sejun was actually taking samples out for analysis. But certainly, as we expose it to the hydrogen, it turns completely black. For the nitrate, once again, consistent with making silver nanoparticles. So he wanted to make sure this was absolutely positively true. So he redid the experiment without mixing. And when you do that without mixing, then these black particles accumulate at the interface. So then he was able to collect those particles and analyze them by XRD, and they are absolutely positively silver metal nanoparticles, silver zero metal. All right, so that appears to be what's happening. Another confirmation of this is by visible light absorption, just a UV-vis spectrometer. These are now those solutions diluted in methanol to be very low concentration. But then the reason is because he was looking for this silver nanoparticle plasmon resonance peak, which is known to occur in the visible, and has to dilute it so it's not black. And sure enough, there it is after exposure to the hydrogen in the case of the nitrate mixture. All right. In the case of the bistriflamide, no plasmon resonance peak. All right, so consistent with the visual observations. The other thing he did with the bistriflamide mixtures was to make sure that after exposure to the hydrogen, that the silver was still able to complex with an olefin. So in this case, he just added some liquid olefin. He added 1-hexene, and you can see the growth down here in the absorption for the complex. So this increase in absorption down at, whatever, 270 or whatever nanometers, this is the complex between the silver salt and the olefin and hexene. All right. And so that happens just fine before you expose it to hydrogen, and it happens just fine after you expose it to hydrogen. So we're still able to complex the olefins after we expose to hydrogen, consistent with the selectivities and permeabilities remaining constant even after hydrogen exposure. All right, so I hope that I've convinced you that silver plus is reduced to silver zero for nitrate ionic liquids, but not for the bis-trifluolamide mixtures. And so then, of course, the question is why? And so we found some nice work in the literature where folks had looked at Raman spectroscopy to understand the environments for bis-trifluolamide and nitrate, looking at those various stretches. And so that's what I'm showing here. So this is the bis-trifluolamide. And so what has been identified in the literature is this peak at about 743 or whatever corresponds to free bis-trifluolamide anions, whereas the one down at 755 corresponds to aggregates of bis-trifluolamide. And so you can see that when we don't have any silver salt in there, we only have free bis-trifluolamide. But as we add silver salt, we see a growth in the peak corresponding to the anion aggregates. So what happens is when you add that silver salt, you're getting aggregates of bis-trifluolamide anions around silver. All right. Those aggregates do not prevent an olefin from reacting. So here's once again with he's adding the 1-hexene, he adds the 1-hexene, and as he adds more of the 1-hexene, the aggregate peak goes down. All right. So the olefin is able to displace the anions around the silver plus. He looked at it at various temperatures. This seems to be true even over, well, we went from like room temperature up to about 74 centigrade. All right, so then the nitrate is a different case. The Raman spectra, the first thing, if you look over on the right, the rightmost peak actually is nothing to do with the nitrate. It's just cation CH2 and CH3 vibrations. So we got to get that out of our mind. But then what's been identified is free nitrate at around 1035, all right, wave numbers, and that the peak around 1045 is actually identified in the literature as cation anion pairs. So on the left is what we get from our mixture with various amounts of silver nitrate added. So the peak on the right, that's just CH2 and CH3 stretches. So what we get is that as we add silver, we actually see a growth in the shoulder, which would correspond to a growth in the amount of free nitrate. All right. So this is exactly opposite with what we observe for the bis-trifluolamide, in which case the silver caused aggregation of the nitrate, of the bis-trifluolamide around the silver plus. All right. So clearly there's something very different happening in the nitrate and the bis-trifluolamide cases. In the bis-trifluolamide case, we see aggregates of bis-trifluolamide around the silver, and it doesn't degrade when exposed to hydrogen, whereas in nitrate, we don't see these aggregates. So the question is, what are these aggregates of bis-trifluolamide doing? All right. So, we could potentially be suppressing the reduction of the silver plus to silver zero, right? The reaction over on the left. This is an equilibrium reaction, but I could be preventing the forward reaction from occurring, right? Another thing that I could be affecting is the nucleation of silver zero atoms, all right? And another possibility is the growth of those nucleated clusters growing into larger nanoparticles. And so the schematic in the middle is just sort of, just a qualitative representation of what happens in the growth of nanoparticles. So what we did was we did a seeding experiment. So we actually put our mixture of bistrophlamid with silver bistrophlamid into a test tube where we had plated it with silver zero. We had plated it with silver metal. All right. So introduced seed particles and then exposed it to hydrogen. And lo and behold, when we have the seed particles in there, it starts turning black. So if we have seed particles in there, then we do not prevent the reduction of the silver plus to silver zero. So what this tells us is that the aggregation of the bistrophlamid around the silver plus is preventing the nucleation of silver zero atoms into particles, into nanoparticles. And that's the mechanism for suppressing the formation of the silver zero nanoparticles. All right, the last thing I want to show you is just some preliminary results. Everything I've shown you up till now has been pure gas permeability. So we do them one at a time, right? This is the normal way that the membrane people do things. So, we measure ethylene permeability, then we measure ethane permeability, and we say the selectivity is the ratio of those two things. All right. But for practical applications, we need to verify what happens when we have gas mixtures. So these are the results for preliminary results for mixtures of ethane and ethylene. All right. And so the pure gas permeabilities, the selectivities we would expect for the 1 molar silver bistrophlamid based on the pure gas permeabilities is about 5. It's these circles, all right? But then all the other filled in ones are various different compositions of ethane and ethylene. And what are those selectivities that we actually get? And they're somewhere between 4 and 5. In most cases, they're a little bit lower, but not substantially lower. So we were very pleased to see this. What this suggests is that the presence of the olefin perhaps increases the permeability of the paraffin just a little bit, decreasing the selectivity a little bit, but still we get decent selectivities. What's shown here is the ternary mixture. So this is where I've got a third ethane, a third ethylene, and a third hydrogen, okay? And these are the permeabilities of those 3 species as a function of time. Sorry, not 3 species, just the ethane and the ethylene permeabilities, and then the orange is the selectivity. And so this is this is 2 weeks. This is a very long time where we're permeating with exposure to, rather high amount of hydrogen. The permeabilities bounce around a little bit. It looks like the ethane permeability is increasing a bit as a function of time. And so we're losing a little bit more in our selectivity than we would like. So this is something that we're investigating further, but certainly this is much, much better than what had been observed in that silver BF4 polymer membrane data from the literature that I showed you earlier. All right, so with that, I'd like to wrap up. I've just want to say that these facilitated transport olefin paraffin separation using these silver salts with ionic liquids is nice selectivities and good high permeabilities because we're permeating through a liquid, and that we're now able to do this by choosing the right ionic liquid and the right silver salt. We're able to do this in the presence of hydrogen. And this is important because, hydrogen's always there because we're making the olefin from the paraffin, which then produces hydrogen. By using the silver bistrophlamid or other bistrophlamid ionic liquids, it protects the silver from reduction by hydrogen through suppression of nucleation. So this is the mechanism by which we're suppressing that silver zero formation. And then to our knowledge, this then is the first intrinsically hydrogen stable facilitated transport membranes for olefin paraffin separations that have been developed. So with that, I want to thank our funding source, which is this National Science Foundation Engineering Research Center, and the people who did the main work here. Most of the stuff I showed you was done by, say, June. And like I said, the last little bit here was done by Maggie.